Is my screen visible? Is my
Yes,
screen
visible,
visible?
sir.
Okay, okay.
Yes, visible.
Good. Oh, thank you. Good morning to all. My name is Gaurav Kumar, and today I am going to present fabrication of driver circuit and sensors for converter applications. I am a PhD scholar at NIT Rourkela right now. These are the contents of my presentation. Firstly, we go for the driver, what is driver and why it is needed. Then we go for the two driver circuits. The first one is TLP-250 driver circuits. I I go for the details of its specification and its pin details. Then we go for the schematics and how its PCB is designed in the KiCad software. Then I will show you the testing and its results. Then I will go for the IR2110 driver circuits. And again, I will discuss about its schematic circuit and its PCB design. Then I will go for its testing and results. Then we go for the sensors designs. In sensors designs, basically, we have considered two sensors, voltage sensor and current sensor. And I will tell you the process of designing the voltage sensor and current sensor and its specification also. And then we design the voltage sensor and current sensor on the PCB also. Moving to the next slide, driver. Why MOSFET get driver is required? When we have to when we have to turn on or turn off any MOSFET switches or IGBT switches, we want the driver circuit because the microcontroller or the the Arduino board which we are using for the PWM pulse generation, actually it produces the output which is around 3 volt or 5 volt. Okay, but it is not sufficient to drive the MOSFET or IGBT switches. So that's why driver circuit is needed. What are the challenges we can face if we connect the direct microcontroller or Arduino output to the gate driver circuit? Actually, if we connect the microcontroller output or Arduino output to the gate driver circuit, then actually in the PWM output pin and gate terminal and a parasitic inductance actually appears due to which we can see there is some distortion in the get to source voltage waveform, so that the proper switching cannot be happened. And also the if you see the output of microcontroller or any Arduino, then its output current is very low. It is in the range of milliampere. So that current is not much more sufficient to drive the switches, because if we want to drive the switches, then we have the get to source capacitance in the switches. We have if we have to turn it on, then we have to charge it, and when we have to turn it off, then we have to discharge it. So that milliampere of current is not that much sufficient to charge and discharge the get to source capacitance of any switches. That's why we go for the driver circuit. And uh, also due to the means microcontroller and Arduino board has the limited drive current source and sync capability, due to which the switching speed is also becomes very slow, and the losses in the switches, due to which it becomes more and efficiencies reduces. Okay, so that's why driver circuit is needed. So basically, there are three purposes for which the driver circuit is required: for signal amplification, for increasing the voltage level. Okay, because to drive the MOSFET or IGBT, we have to amplify the voltage up to 12 to 15 volt approx. That's why signal amplification is needed, and that's why driver circuit we want. And also, it provides the load isolation. Actually, it provide the isolation between the microcontroller circuit, which is a low device circuit, low power circuit, and we have the some converter circuit, which is a high power circuit. So what driver does, it actually also provides the electrical isolation between the low power circuit and the high power circuit, and also it improves the switching. Driver circuits are designed to switch loads on and off quickly and efficiently, and which is particularly important in application like PWM for motor control or LED dimming. Moving to the next slide. This is the complete MOSFET model of the this is the complete MOSFET model, means MOSFET or IGBT module. Here we can see there are three terminals, gate, drain, and source. We can see there is a parasitic inductance in internal inductance in drain terminal and source terminal also. And there are three parasitic capacitance between the gate and drain. The other is between the gate and source, and the last one is between the drain and source. Okay. So when we are going to turn on the MOSFET switch, we have to charge the gate to source capacitance. Okay. And when the gate to source capacitance is turned on, then then the d the difference between the voltage gate and drain is something, some voltage appears. Then the there is a current also flow between the gate and drain terminal, due to which the reverse the the capacitance between the G and D terminals is also charged. Okay, so this is the specification for the IRF 540N driver circuit. So total gate charge which is required to charge to turn on the MOSFET is 72 nanocoulomb. Actually, it is the charge which is required to activate to charge the CGS capacitances and CGD capacitances. Okay. And the desired turn on time of the particular MOSFET is 1% of the switching time period. If suppose if we want the switching frequency of 10 kilohertz, then the desired turn on time is 1 microsecond. Okay. So here we can find the charge per time ratio, which is 72 milliampere. That means if we want to turn on the IRF 540 and MOSFET, then per second we have to we have to deliver 72 milliampere of current to turn it on. Okay. Similarly, for if we go for the higher switching frequency like 200 kilohertz, then the desired turn on time is 0.05 microsecond. So the gate current is charge per time is 1.44 ampere. That means we have to provide 1.44 ampere of current per second to turn it on the MOSFET when we go for the higher frequency. So here we can see if we go for the higher frequency, the if we go for the higher frequency, the current requirement is increased. Okay, so at that time when we go for the higher frequency switches in the converters in any applications, then we go for the more strong driver circuit. Okay, which can provide the more output current. Moving to the next slide. So this is the first type of driver, which is TLP250 driver, and it has basically 8 terminals, and it is also known as optocoupler. Okay, so these are the specification of this optocoupler. These are the specification like input threshold current, which is 5 milliampere, which is maximum 5 milliampere current. Actually, if we see the TLP250 driver circuit configuration now, then there is a LED device, and at the output terminal there is a photosensor. Okay, so if for turning on that LED, we need to provide the current, which is the threshold maximum current is 5 milliampere. Okay, supply current, which is the maximum supply max current is 11 milliampere. The supply voltage which we can provide to the uh, to the to the terminals of the TLP250 is 10 to 35 volt, and the output current which it can produce is 1.5 ampere maximum. Okay, switching time is TPLH and TPHL is 1.5 microsecond. Here TPLH means TP means propagation delay from low to high, and this is propagation delay for high to low. Actually, when we are giving the, suppose we want to turn on the MOSFET. Okay, so we are giving the microcontroller pulse to the TLP250. Okay, so then at that time we are getting after some time we are getting that output. So what is the time difference between the input and we are getting the output? Okay, So that time is 1.5 microseconds. Similarly, when high to low, when we want to turn it off, then at that time also we get 1.5 microsecond of delay. Okay, this delay occurs because LED is turning on, and after that, after some time, after 1.5 microsecond, the photo detector, photo sensor is sensing that LED infrared light. That's why some propagation delay come. Isolation voltage. Actually, the driver circuit, what it does, I have told you that it provides the isolation between the microcontroller circuit and the converter power circuit. So this isolation voltage is minimum is 2500 volt RMS, and the maximum operating voltage during the normal operation is 630 volt peak, and highest permissible over voltage is 4000 volt peak. If we want to go for the highest, if we want to go above 4000 or above 5000, then we go for the opto isolator drivers. Moving to the next slide. Okay, you can see this is the TLP250 driver circuit. There are total 8 pins, 1, 2, 3, 4, 5, 5, 6, 7, 8. The 6th and 7th terminals are shorted. That we can see 2 and 3 terminals. In these 2 and 3 terminals, we give the microcontroller pulse. The microcontroller pulse input is given from this 2 and 3 terminals. And the 15 volt supply or 12 volt supply we can give to the 8 and 5. This is the 5 terminals. The 15 volt supply we can give to the 8 and 5 terminals of the micro of this TLP 250 driver. And here when we provide the microcontroller pulse, then LED is turned on, and that LED turned on. When LED is turned on, then it it generates some infrared signal, and that infrared signal is actually detected by the photo detector, photo sensor, which is present here. uh, and that photo sensor, according to that intensity of pulse which we have provided to the input, it converts into the corresponding voltages. Okay, so basically optocoupler, what it does is it transfer the information, analog or digital information, from input port to the output port. Okay, uh, here one thing we have to keep in mind, that in between 8 to 5 pin, between pin 8 and pin 5, we have to connect a ceramic capacitor which is of 0.1 microfarad. Actually, it is much more necessary because it it reduces the high frequency noises which are present in the 15 volt or 12 volt supply. And so for noise filtering purpose, the zero point 0.1 microfarad capacitor is needed. Okay, so zero point 0.1 microfarad capacitor we connect across the 8 and 5 terminal. Moving to the next slide. So this is the schematic circuit of the TLP250 driver circuit. Here you can see I have given, and this is the 2 and 3 terminals from in which we have provided the microcontroller pulse. Then between 8 and 5, we have to provide the supply, which is 15 volt supply or 12 volt supply you can and provide. Actually, I have told you the range, which is 10 to 35 volt range. Okay, so 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 between 10 to 35 volt range you can provide the supply. Then we see the some parallel capacitances, 100 nanofarad and 100 microfarad. Actually, this is the total combination is, I have told you the total combination should be 0.1 microfarad between the 8 and 5 terminal ceramic capacitor.
हाँ मेरी लाइफ बिल्कुल अच्छी चल रही है। मुझे तो लोग ये भी कहते हैं कि मुझे तो कोई भी पसंद कर लेगा। वैसे यूँ तो मॉम मैं आपको बाद में कॉल करती हूँ। तुम यहाँ वीकेंड्स में क्या करने आए हो?
Please mute. Whoever has turned on his Mike, please mute it.
क्या तुम मुझे यहाँ हेल्प करने के लिए आए हो?
Please mute it. Okay. So this is the schematic circuit which you should know before designing the PCB. Okay. Well, what should be the resistance? What should be the capacitance value? What should be the supply which we want to give? So all you should know before designing the PCB design. So now I will show you how to design the PCB, how to design the PCB by using the KiCad software. I will design the TLP250 driver circuit. Okay. So firstly, you have to go to KiCad. Then you have to go to new project. Then you have to give some name like we are designing TLP250 drivers. So we go for the TLP250 driver circuit. Then we have to go for TLP250 schematic. This is the platform on which we can draw the schematic circuit. Okay, the schematic circuit means the circuit diagram we have to draw. So firstly, you have to go for the place symbol. Okay, you have to go for the place symbol. You have to click it, and you have to click on the board. Okay, then it actually whatever the library installed in the KiCad software, it will come. Then you have to search the TLP250 driver. TLP250. Okay. Then you have to select it. Then okay, you have to place it. Then again you have to go. You need some resistances also. So we have to write resistor. You just put R, then it automatically come. Now we want some capacitor also. So we type C. We want some polarized capacitor and unpolarized capacitor both. So first we click on the unpolarized capacitor and we take it. Then again we go for the place symbol. Then we took the unpolarized capacitor. So I have taken it again. Polarized capacitor. Actually, polarized capacitor is like electrolytic capacitor, and the unpolarized capacitor is this capacitor. Now we want some terminal block. Terminal block is required to give the input to the TLP250 and getting output from the TLP250 driver. So we have to write some terminal block. Screw terminal block it is. So 1 by 2. 1 by 2 means it has two terminals, and one means one terminal block we are using, and 1 by 2 means two terminal it is. So I have taken. Now I have shown you the schematic which has three resistances. The first one is at input, and the other two resistances R2 and R3 is like this. Okay, so we want three resistances, and we want total three terminals. Okay, the first terminal uh, which we require for giving the microcontroller input. The second terminal which we want to give the 15 volt supply, and the third terminal which we want is to take the output. Okay, so we have to when we go to the R resistor, then press C, then it will be copied. Then you have to just press here. Then again you have to press C to copy and come here. Now we want three screw terminals, so we have to press C, copy. Then we have to press C, then it is again copied. Now we have to connect it. Okay. If you want to rotate it, then please press R, then it will be rotate. And when you want to move it, then you keep cursor on the thing which you want to move, then press M, it will be moving. Okay, so place here. We can change also its orientation. We want to change its orientation about the orientation we want. Okay. So first task is to arrange all those components. Okay, now we have to connect it. So we have to go for the place wire. Okay, here is the option for placing wire. So take place wire, then please click single click, then you have to click double click. Again single click, then double click. Okay, then both capacitors have been parallel connected. The 6 and 7 terminal is shorted, so you have to the output resistance are connected between the 6 terminal and 15. So you have to implement that. And the supply is connected between 8 and 5 terminals, so you have to connect 5 terminals. So the first terminal which I have shown to you is used for giving the input from the microcontroller pin, and this is the supply terminal around which I will apply the 15 volt. Okay, and this is the output terminal which we get output terminal from which we can take the output. Actually, the output which we got is actually the amplified version of the input pulse. Okay, the input pulse peak which we are giving is around 3.3 volt peak. So after amplification, I will get around the 14 or 15 volt amplified peak. But the nature is same. Okay, so this is done. After making the schematic circuit, you have to go to the tools and you have to go to the annotate schematic. Annotate schematic means it will give the name of it will give name to each and every components which we have used, like resistors, two terminal or capacitor which we have used. It will give name to them. So annotate it, then close. Then you can see name is coming. This is screw terminal one J1. PLP250 name is also U1 R1. Okay. You can also change its text values, what resistances you are using. If you like in R1 we are using 1 kilo, so you can write 1 k. Okay. Similarly, the unpolarized capacitor which we are using is of 100 microfarad. So you can write 100 microfarad, and its rating is some 50 volt I have used. So I have written 100 microfarad 50 volt. Similarly for C2 you can change. We have used zero point 0.1 microfarad, and it is also 50 volt. So you can write it. Okay, similarly for resistance R2, it is 10 ohm, so you can write 10, 10 R for R3, which is 1K. Okay. After writing all the names, you have to go to the generate netlist file. Generate netlist file is necessary because it tells us about how the components are connected with the socket. So it is needed. Generate netlist file. Okay. Then you have to go for the assign footprints. Assign footprints is required because whatever the resistance or capacitances which we have used, actually we have to you have to give the proper footprint of this. So we have to go for the assign footprints. So these are the components which are showing. Right now we have to select its footprint. Okay. So the first one is zero point 0.1 microfarad 50 volt capacitance, which is actually unpolarized capacitance value is 0.1, which is the disk capacitance, and its rating is 52. And the polarized capacitance value is 100 microfarad. 50. Frequency. Okay, so what is the footprint you have to select? Actually, there are two type of footprint. The first one is TSD through hole, and the second is SMD, the surface mounted device. When we see any PCB circuit on which is the all the components are surface, or all the components are mounted on surface, at that time we choose the capacitor surface mounted device section. And when we see that PCB which have some drilling, okay, in which through drilling we place the component, then we have to go for the capacitor THT. Okay, so in capacitor THT there are three types of capacitance. You can see the first one is axial, then we see the radial capacitances, and the last one is the axial disk capacitances. Okay, so polarized capacitor, what we need is radial capacitances. Okay, so radial capacitances in which we want radial 10 mm and pitch of 2.5 mm capacitance. Then please press OK. You have to press double click, okay, to select this footprint. You can also see this footprint in this section. You can also see this footprint. This is like that. Then you have to select the resistance footprint. The resistance footprint, you have to go to resistor THT, resistor THT, and you have to select some 6.3 mm 207. This one. Okay, you have to double click it to select. Actually, I am pressing single click and I am pressing the OK. That's why it is closing again. Okay. So the same for the other resistor also, and the 0.1 microfarad capacitor. We have to select the disk capacitor, capacitor THT again. We have to go. We have to select some 5 mm. This section I have to, this section 5 mm. If you can see this, the resistor same footprint we have to copy and paste here. The screen terminal we have to go to terminal block, which is here. We have to select 5.08. And then actually all these devices, all these footprints which we have selected, actually you have to go to the capacitance data sheet. You have to go to the resistance data sheet which you are using. On that data sheet, you have to find what is the uh, distance between LED, what is its diameter, what is its pitch. You can see it. So footprint is very much essential. So it has to be properly selected. Okay. Then you have to save the selection. You have to, okay, you have to go to the OpenPC. You have to use update from schematic. Update in this type of interface. You have to use it. Now you have to arrange. You should you have to arrange according to your schematic. If you want, if you press R, then it will be rotated. This is the input resistances. Now you have to connect all these. So you have to connect it with the copper trace. So you need to set here the copper width. Here we can I'm using some 1.5 mm copper width. So you have to first add 1.5 mm copper width. You have to press OK. Then 1.5 mm is selected. Now you put the copper pressing of copper. You have to firstly you have to select the bottom copper because if you are designing some PCB is which is of fluid version of PCB in which the component is placed through drilling. So you have to select the bottom copper. If you want to make some PCB which is surface mounted PCB, then you have to select the front copper. Okay. So I have selected the bottom copper. Now you have to connect all those things according to the lines. Now you have to select edge cut because you have to cut the PCB also. You have to select here edge cut. Then you have to select the polygon. You have to draw that polygon cutting. Then the PCB is made. You can view in the view section, 3D viewer. You can see this is the PCB which is made. Then we have to go for the printing of that PCB. How we print? We have to go in the file section, then print section. Print section. When we go to the print section, we have to print only bottom copper layers because we don't want the copper layer in the front because it is used for the surface mounted PCB. So bottom copper is selected. Bottom silk you can also select because whatever the names you are saying that is true terminal U1, J1, all will come if you select the bottom silk. Edge cut you have to select and you have to select the bottom mask also. Actually, bottom mask is something which actually covers the copper traces to the bottom layer so that it can't go into the corridor or anything. Okay. Then you can see the print preview. This is like that. Then you have to print it, and after printing, the you have to print it on copper board. Then you have to do the copper etching process. Then you have to drill or where the location is given. And according to after that drilling, you have to place the components and solder them. Then PCB is designed. Okay. So if you want to go to the manufacturer to make the PCB, then you have to share some data so that they can they can print you and they can send you uh, the PCB. Okay, so you have to go to the plot and you have to make some Java file. Okay. So front copper is not needed, front paste, bottom paste not needed, front self is also not needed. Bottom self is needed, bottom mask is needed, edge cut is needed. Okay, so all these four information we can plot and we have to give it name to save it. Then we have to save. So we are saving where we have used it before. And also we have to save the drill files where we have to drill the components, drill on the PCB so that we can place the components. So then the drill file is also. So drill file is also generated. Okay. So that Java file which is saved in the EMP2 on the desktop. See, this is the Java file. Okay, this file is you have to share with the manufacturer so that they can print you and they can deliver you the PCB. Okay. That you have to share with them. So after making a schematic and designing, this is the PCB board. After that, this is the PCB which TLP250 driver is, and here we have tested. You can see the microcontroller pulse, which is giving you the TLP250 driver is approximately 3.34, and with the help of 15 volts of it is amplifying, and we get the output, which is also pulsating in nature, and you can see the output is the peak is 40.2 volt, which is very much sufficient to drive the motor. Moving to the next slide, IR2110 driver circuit. This is the another driver circuit which we use for the driving the MOSFET. It is used when we want to drive the half bridge circuit or full bridge circuit, in which two MOSFETs are in a particular leg or IGBT in a particular LED, then we have to use the IR2110 driver socket. It has the voltage range of 500 volt to 600 volt, and it is also designed so that it can tolerate the negative transient voltage, which is mostly common when we go for the fast switching of the devices. It is due to the parasitic inductance, and d by dt comes due to the parasitic capacitances. So it is also d by dt immune. The gate driver supply range is from 10 to 20 volt, and it is also 3.3 volt logic compatible. Means you can give the microcontroller pulse is 3.3 volt to 20 volt to it. Okay, and also under voltage lockout for both channels. From this IR2110 driver circuit, we can drive the two switches. One of the high side MOSFET and the other is the low side MOSFET. And if some error comes, then uh, suppose if the voltage is insufficient to drive both the switches, then it under voltage lockout for both channels. The output will not. Moving to the next, this is the pin diagram of the IR2110 driver circuit. Here VDD is the supply voltage. Here we can give the 15 volt supply voltage or 12 volt supply voltage. HN stands for the microcontroller high pulse, means the pulse by which we drive the higher side MOSFET. Okay. Higher side MOSFET. It is trying to logic into the shutdown. And and HO is the output of the higher side MOSFET. LO is the output of the lower side MOSFET. VCC is the 5 volt supply. This is the COM for the common ground. Okay, moving to the next slide. This is the schematic circuit of the IR2110 driver socket. Actually, if you see the lower MOSFET switch is actually the lower MOSFET switch is fixed driver channel, and the upper is the floating driver channel, because you can see it's the source terminal is not at the ground potential. When the lower switch is turned on, then the source is at the ground potential. But when the lower switch is turned off, then the source is not at the ground potential. So that's why it is called the and floating channel driver circuit. So in that case, you have to use some bootstrap capacitance to give the supply to the upper switches. Okay. So in bootstrap capacitances, you can see C1 and C2 here. These are the capacitances is of the bootstrap capacitances. Okay. So when we supply the VCC or when we supply the VDD 5 volt and VCC 15 volt and 5 volt, then through the bootstrap diode, which is D1, these capacitance gets charged. Okay. This capacitance gets charged up to the supply voltage, which is we have given to the 15 volt. Okay. And when we try to turn on the Q1, then in the next half cycle, when and it is fully charged, then the bootstrap diode becomes reverse bias, and these capacitances should discharge through this path R1, and this discharge through the HO, and it will go to the Q1 output, and it will turn on the MOSFET. Okay. So these are the schematic circuit of the IR2110. This is the PCB design, and this is the final output. Okay. This is the IR2110 circuit which we have designed in our lab, and here we have tested. And here we can see with the help of IR2110, we can drive both switches of a particular leg simultaneously at a particular time. Okay. So here we can see we are providing two input pulses of which we are getting through the microcontroller, which is in the complementary version, and we are giving that pulses to the IR2110, and we are also giving some input which is 1550 volt supply. This is the supply circuit which you can see. This is the 1550 supply. Means 15 volt and 5 volt they are providing to this IR2110 to work. Okay, then we are getting two output. The first one output is high side output, and the second one is the low side output. You can see, and you can see the output. The high side and low side both are complementary pulses, and both are amplified. See, the high side pulses is amplified to 13.6 volt, and the other side is 14.8 volt. So these are the sufficient voltage which we can from which we can turn on the MOSFET. Okay, into the next slide. Voltage sensor. Okay, how voltage sensor is designed. So this is the voltage sensor which can sense the voltage as bipolar voltage it can sense, and it can sense the voltage around plus minus 10 volt to plus minus 500. Okay, and this is the voltage sensor which actually works on the principle of Hall effect. Hall effect voltage sensor is something when we give some input to that sensor, then it will convert. If we are providing some voltage or current to that Hall effect sensor, then it will convert that voltage or current into the magnetic field. Okay, and that magnetic field which is sensed by the transducer, and transducer will convert that magnetic field strength into the corresponding voltage and current. But whatever the intensity of voltage or current which we are providing in the input side, and on the same magnitude of intensity, the output is produced in terms of voltage and current. Okay, so these are the specification. You can see the primary nominal RMS current is 10 milliampere. Okay, and primary current measuring range is plus minus 40 milliampere. The measuring resistance, which is for if we are providing 12 volt plus minus 12 volt supply, then at if IPN is plus minus 10 milliampere maximum current, then the measuring resistance which we can select is between this range 30 to 190 ohm. And for 14 milliampere current, 30 to 100 ohm resistance I have to select. For if we supply plus minus 15 volt, then according to that the ranges varies. And the secondary nominal RMS current is 25 milliampere, and the conversion ratio which is of this voltage sensor is 2500 is to 1000. So this is the turns ratio, 2500 is to 1000. Okay, moving to the next slide. So this is the voltage sensor. There are three terminals in it: M, positive, negative. Positive, negative, from which you can provide the plus minus 15 volt supply or plus minus 12 volt supply. M is the measured pin, and from HT and minus ST you can provide uh, the voltage which you want to sense. Okay, so this is the overall diagram LV25. Suppose we want to sense the AC voltage. So if the AC voltage is connected with the R sense resistance, then LV25 voltage sensor, then plus minus 15 volt supply, then M is connected with some measuring resistance, and then it is connected to ground. Okay, when we design the voltage sensor, the first thing which you have to keep in mind that you should design your R resistance so that your the primary current should be near to the 10 milliamp. Then at that time your voltage sensor should be properly designed, and it has much more accuracy, because it is written in datasheet also that you have to select the primary nominal RMS current uh, approximately within the range of 10 milliamp. Okay, so how to design it? So for maximum accuracy, IP should be 10 milliampere. I have told you. So IP is fixed. Okay. And so due to turns ratio, we know the turns ratio is 2500 is to 1000. So the turns due to the turns ratio, the output current is 25 milliampere. Okay. And output voltage VS is also fixed, because for C2000, if we want to design, then it is 3 volt, and for Arduino, if we want to design, it is 5 volt. So we only have to design the resistance Rp and the resistance Rf. Okay, the resistance Rp means the primary resistance, and the secondary resistance which is Rs or Rn you can say. So how to design Rp? So Rp is Vp by Ip. Vp we know we are designing right now for 50 volt. Okay, we want to sense the 50 volt voltage. So Vp is 50 volt and Ip is 10 milliampere, because it is fixed. We have to fix it because for maximum accuracy you have to fix IP is 10 milliampere.
So VP is 50 volt, IP is 10 milliampere. So RP we need is 5 kilo. Okay. And the RM is VS by IA. VS is also fixed. Let's suppose we are designing for the Arduino, so it is 5 volt. If we design for the C2000, it is 3 volt, so 5 volt, and IS is fixed. It is 25 milliampere due to turns ratio. So RM is 200. Okay, so you have to, if you want to sense the 50 volt voltage, then you have to fix RP 5 kilo ohm and RM 200 ohm. Okay, then you can also find the wattage of the RP resistor and RM resistor which you are going to use. The WP wattage of the first resistor is 0.5 watt, you can see, and WM is the 0.125 watt. So when you design the voltage sensor, which can sense the 50 volt voltage, you have to you have to you have to use the resistance RP 5 kilo ohm, RM 200 ohm, and you have to use zero point 0.5 watt resistor of 5 kilo ohm and 0.125 watt resistor of 200. Okay, moving to the next slide, current sensor. So this is the current sensor, which is also works on the principle of Hall sensor, Hall effect sensor. Similarly, the case when we provide the input, in this case, the input is some current, which we provide through some wire. Here you can see some hole is present. Here you have to own some wire, and in wire some current flows, and this is the input of that current sensor. Okay, so when current flows through it, it will generate some magnetic field, and due to Hall sensor, and when magnetic field is produced, the transducer convert it into the corresponding voltage and voltage of current signals. Okay, then we can take the output according to that. Okay, in this case also in current sensor we want the output should be 3 volt or 5. In If any sensor you are designing now, voltage sensor, current sensor, at last the sensed output you have to give to the microcontroller or Arduino you have to, which is 3 volt or 5. So at that time you have to, since the secondary voltage is always fixed. So here we can sense the maximum current of plus 50 ampere to minus 50 ampere, and these are the specification which is given. Okay, these are the current sensor terminals. These have only three terminals, plus minus. Here you can give the plus minus 15 volt supply or plus minus 12 volt supply, and here you only have to design the measured resistance R. Okay, so this is the direction of current. If you pointed the wire in this direction of current, then the output, which is the secondary current, which comes out to be positive. And when you are holding the wire in the opposite direction of that arrow, then is comes out to be negative. Okay, so IP is positive when you hold the wire in the direction of arrow, and IP is negative, and is also negative when you hold the wire in the negative direction. Okay, so this is the design procedure. Uh, we are supplying plus minus 15 volt, and the maximum range is plus minus 50 ampere maximum. So for this specification, Rn should be between 50 to 160. Okay, the measured resistance, with the help of a specification, we can see it is written in specification for plus minus 15 volt supply and 50 ampere maximum current. If you want to sense, the resistance would be between 50 to 160 ohm. So I have selected 125 ohm. Okay, PS is fixed 3 volt and 5 volt, and we want to design this current sensor for primary current should be 10 ampere. Okay, so secondary current, what it will come? Secondary current will come VS by RM. VS is 5 volt and RM measured resistance is, I have choose 125 ohm. So the IS is 0.04 ampere. And we know it is like transformer, so the formula is NPIT is equal to NSIS. NS in current sensor, the in current sensor, the secondary number of turns is 1000. Okay, secondary number of turns is 1000. So you can easily find the number of turns of the primary. Number of turns of primary is NP is equal to NS into IS divided by IP. So 1000 into 0.04 ampere divided by 10 ampere is equal to 4 turns. Okay, so so the two things which we want for the designing of current sensor is the number of turns of the wire which we are putting on the whole of the current sensor. So the number of turns would be the 4 turns, and and the secondary resistance which we are using is of 125. Okay, and this should be of 0.2 volt. Moving to the next slide, this is the schematic and PCB design, schematic of the current sensor circuit, and this is the PCB layout, and this is the print view, and this is the current sensor which we have designed in our lab. Okay, this is the PCB track with table. Okay, uh, actually we have in when we have designed the driver circuit, I have taken some 1.5 mm of copper trace width. Okay, so when you are going to select the copper trace width, you know about the current which we are flowing, which flowing through the circuit of the driver circuit. Okay, when you are designing any converter or inverter circuit through the keycap, you should know about the current which it is flowing through the circuit. Okay, according to that, you have to select the copper trace width. Okay, so here it is written if you are using 1 ounce copper, it is in mm and it is in mils. So if you are using 1 ounce of copper, then for 2 ampere of current it is 0.76 mm. For 1 ampere of current it is 0.38 mm. Okay, according to that you have to select. And for 2 mm of 2 ounce per foot square of copper, copper lead PCB, then you have to select according to current. These are the of trace width. Okay. So now I will show you the PCB design of IR2110. This is the IR2110 schematic. You can see. Okay. So whatever the diode value and whatever the resistor value I have shown, it should be properly taken. Then after you can get the proper output. This is the PCB layout. This is the PCB layout, and this is the 3D view of the PCB of IR2110.
Now I want to show the sensor schematic. Now you want to, I want to show you the sensor schematic. This is the sensor schematic diagram. This is the PCB circuit. Okay, and this is the 3D view you can see of the sensor. So that's all from my side. If anyone have any question, then they can please raise. Am I audible?
Yes, audible. Thank you, sir.
Yes, sir. If you ask, if you have any question, then you can ask. No one has asked. No one has any questions.
Hello, sir.
What?
I'm audible, sir.
Yeah, you are audible. Please tell.
Very good evening, sir. I'm Chandrasekhar here from Salem Vinayaka Mission Research Foundation.
Okay.
I have
Please
a
ask.
small doubt, sir.
Yes.
For measuring any parameters, how do we understand that those way of sensor can work? Like I want to measure the blood. Like we have two type of color. Like one is for artificial color, one is human blood color. I want to deduct that human blood cells. So how we can understand with our voltage or current parameter to detect this is human blood while scanning, not through any measuring with internal meters directly through physical way. Like human, how we can identify this?
You are right. Actually, you are right. You are asking some related to biomedical field. Actually, I have done whatever I have done is it is mostly related to some power electronics. Okay, in which only voltage and current is sensing is required. Okay, voltage sensing is required, current sensing is required. Sometimes you can sense the irradiance of the solar panels also. The only that thing is required. And if you are asking for the blood, then it is I think it is related to some biomedical field. I don't sorry.
Not like this, sir. Like there also, I need to identify that
Hmm.
intensity of color or
Okay, okay.
light, how we reflect through IR sensor or ultrasonic sensor. Same
Yeah.
intensity will return back to our ultrasonic sensors. Then we can identify through our power electronic device or electronic device
Okay.
how much intensity of our human blood havings and how much intensity of normal
Yeah.
artificial color we have. Because
Okay.
as a light rays is reflecting, they have
Okay.
also seven rays, like group of rays, like white colors. From there also we can define the intensities. So if possible, miss, can you help me out with your laboratories?
Yeah, I can help you. Actually, whatever the sensor you are using now to detect the artificial color and intensity, what you have told to me. Actually,
Yeah.
at last we have to convert it into the voltage, because
Yes,
at last we have to sense it through the microcontroller or Arduino board. An Arduino
yes,
board or microcontroller only knows 3 volt and 5 volt. Up to that voltage they know. So depending upon the voltage range now, it can identify the intensity. Let's suppose your color is very much dark, so its intensity should be around 3 volt. If it is
mm,
too low, then it is around 1.5 or 1 volt, like that. Okay. So depending upon the output voltage, you can find that intensity of darkness or anything. So first you have to convert it into the voltage output. So you have to use some transducer also so that it convert it into voltage range. Okay.
mm.
You have to find some sensors which it can convert into the output voltage.
I plan to design like this sensor. Still, it is not existing in my lab and also maybe outside, maybe other institution. So if possible, miss, just let me know, sir. I'll get
Okay,
in
okay,
touch with you.
okay.
Thank you, sir. Thank you so
Yeah.
much.
Is any more questions from the audience side? Okay, I think no more questions from you all. So I'm now stopping the recording session.